Hi everyone, my name is Tadeas Kriz, and I'm going to tell you about Kotlin-Native. I hope that all of you are Android developers. If not, go. Now, stay. I need all the people I can get. So first, I would like to do a little advertisement. No, not really. Just want to thank TouchLab because they are the main reason that I am here today. But the reason I want to talk about TouchLab is that we do a lot for KMP, and we try to do as much for community as possible. When the KMP was young and there was like a need to get a starter project, start a template to get your projects off the ground, we made CamKit. Popular, JetBrains recommending it, great. Then once you have your projects, you need to get them to the iOS side somehow. We've seen that, we had the same issue, so Cambridge, depends on how you say it, become a thing. Then, the other thing was, okay, Swift and using Kotlin from Swift, it was a pain. Ask me how I know. So we made Sky. At first we wanted to, it is a big project, so we wanted to do something that we can sustainably develop. So it was supposed to be paid, but we've seen that that's not the way. We need to make sure that it's still developed sustainably so we can continue on it. But we made it open source. So as of last, 2 weeks ago, it's open source. So if you haven't seen that announcement and the trillion of emails that our marketing team's been sending your way, go and get Sky for your KMP project. The reason why I put this in the front is that we're now looking what to solve next. We see issues in KMP world. There's certainly a lot of them, and we don't want to build in vacuum. So there's gonna be one issue that will be okay, what's the major one? And we want to know. So if you could, please come to our booth or just message us on socials or anywhere. Let's chat, let's see what your problems are or why you can't get KMP off the ground in your company. We really need to know all of that feedback. We also work closely with JetBrains, so we can share with them if it's something with Kotlin itself. Now I'd like to give you a little bit of background for me. So I always worked with VM-based things before going into iOS. So I started with PHP, then I did some desktop apps in C#. I'm a little bit ashamed about that. Then I did Android for many years. Unfortunately, probably, I got into a point where I wanted to do iOS. I liked iPhone, I got an iPhone, I wanted to do iOS. But once you go into iOS, you find that a lot of the things you've been used to don't really work in native. And I struggled a lot. And so this talk is my way of kind of paying forward all the help I got from the community back then, and hopefully introducing you to okay, what is different, what is similar, and what to do about it. Let's start with differences and similarities. So we're gonna compare JVM Kotlin and native Kotlin a little bit, and we're gonna do native compilation, linking, and execution in more depth. I'm not gonna cover everything, and a lot of what you're gonna hear is targeted at Kotlin-Native on iOS, or Apple platforms in general, kind of. But I'm not gonna look at Linux or Windows at all. They all have similar things, so it will apply somehow, but not everything will be the same. And the last thing I want to share with you are some of the best practices I've learned along the way, and something you should keep in mind when you're doing KMP. So what do you think? If I leave this open, will I spill it in my MacBook? The probability is high, but it's easier to drink, so I'm gonna try it anyway. Let's go to comparisons by steps in the development process. We start with compilation, because writing code, that would be the first step. That's kind of the same, right? It's a different language, sure. It's a different framework, sure. But overall, you still write code. The compilation is the first part where you find a lot of differences. So in JVM, we start with the source code, and that gets compiled into bytecode. And then the bytecode is kind of your final thing that you deploy, you distribute, and it's gonna get run by the JVM interpreter. In native, however, when you have source code, oftentimes when you compile it, you see the resulting executable library. So it kind of abstracts away what's happening inside. And even this is kind of abstract, because there's more things happening. But the main important thing is it first takes the source code, file by file, and compiles it into object files. Those object files, they are native code already. So they could be read by a machine, but they're not executable by themselves, because they're missing a lot of information. And then you take those object files and also libraries to link them. That's still running on your machine, so then link them into an executable or a library. As you can see that this additional step is, as I mentioned, it's often hidden from you, so you just run the compiler, but it's really important to know what's happening behind the scenes. Another thing that's different between JVM and native are build configurations. You may be familiar with the variants of flavors on Android, right? But on Android, even when you have a debug or a release variant, they don't differ that much. And you can even say, OK, I want this release to be debuggable. Maybe you just do obfuscation. But on native, there's a huge difference. So native, let's focus on debug and release. Obviously, there's more you can do. You can configure whatever you want. But those are the main things. So with debug, you usually have a large binary, because it has all the debugging symbols, all the debugging information that you need to take with it. It's also not optimized, so it's slow. And also, optimizations often cut down on the code, so it's contributing to the large binary as well. However, it is debuggable. And by debuggable, I don't mean that you wouldn't be able to debug release. You can. But because of all the optimizations, the code no longer follows the flow you wrote. So when you put a breakpoint somewhere, it may not stop there because that line may not exist anymore. Or when you step through your code, it will be jumping around because of the optimizations. And it's also usually faster to build. I say usually because if you build Swift compiler, for example, in debug, it takes way longer than in release. There's oftentimes additional configuration in the middle. I think it's release with deb info, something like that, or rel with deb info. It's kind of a combination of both worlds, and it's usually for large projects where you need to debug it. So you have the debug symbols in it, so it's large, but it's not slow because it's gone through the release, and it's also faster to compile. Again, applies to large projects. For release, as you can see, it's kind of the opposite. It's basically the same thing, just in reverse. So we have longer to build. Again, depends, but in most projects, longer to build, because it needs to go through the optimization process. It needs to link everything. It needs to get all that out of the way. You have the limited debugging. Again, you can debug release. That's fine. But it won't be a good experience. Trust me on that. Better performance, optimizations. Lower size, optimizations. As we covered in debug, go in reverse. Another fun thing that I've struggled with a lot is build targets. Being on JVM, I just built it and it works everywhere. And I never did JNI much because of all the weird stuff that comes with it. And then on native, I'm like, oh, what are those? So on native, you may have heard about this thing called triplets. They are not used universally. As you might learn that with native, there's no kind of a standard. I mean, there are standards. There's an infinite number of them. This one is kind of used on the iOS and macOS, all the Apple platforms. It's sometimes used on Linux as well, but your mileage may vary. The triplet describes your binary, so when you build it, it describes what architecture it will run on. The vendor, that's kind of weird because it's doesn't really matter usually. It's usually just part of the platform information anyway. So the platform says, OK, this is iOS binary or macOS binary. You won't be able to run one on the other in any way. Well, except what Apple did with their Apple Silicon, where on the Mac you can run it But. And then environment, that's kind of optional thing, where it allows you to specify, like, for example, simulator on iOS is an environment. It's still iOS. You use all the iOS SDK and everything, but it's only going to run on a simulator. So, for example, out there, I don't have a simulator shown, but down there we have triplets for iOS and tvOS. The environment would be another like dash simulator next to it. And then those binaries won't run on your devices, and vice versa. It's also the way they make sure that when you somehow acquire a package from iOS, you won't be able to just run it on your simulator and maybe like crack it or something. Now, when you have those triplets, right, those they are about one binary. But you oftentimes need to target multiple platforms. It's less relevant today because, like, for example, iOS, tvOS, watchOS, they all have just one architecture. But if you're building macOS, you're still gonna need to deploy two architectures. That's the ARM and Intel. So one way to do it is universal binaries, sometimes in the old days called fat binaries. They do support different architectures. They, quote unquote, support different platforms. But they are huge. So if you're deploying them somewhere, you're gonna deploy all of them. So if your app is large like Xcode, you're gonna deploy 2 Xcodes, essentially. So you're deploying everything twice. And there's no way to kind of say, oh, I just want that. Not really. Your users could do that, but if you're assigning your binaries, and you should be, then they break the code signature. I included how it kind of looks, but it's not really that important unless you're like really diving into it. So it's just, okay, the fat header that describes what architectures are going to be there and where to find them, where in the binary, and then architecture 1, 2, 3, whatever. You can go as far as you want, I think. The modern way is XC frameworks. So XC framework, funnily enough, it's just basically a funny way to call a directory on macOS. They call them bundles. It's a directory with extra steps and an extension. They have direct support for different platforms. So how many of you used XC frameworks with KMP? Okay. How many of you used fat binaries with KMP? That's about the same. I don't know if there's much overlap. Hopefully you all use XC frameworks now. They do have their own problems. The size is, I wanted to include that because like the size doesn't matter that much. It really depends on how you deploy the app. If you're deploying through App Store, for example, App Store will make sure that you're not deploying everything. But that often applies to the fat binaries as well. And also, it doesn't really apply at all because there's just one platform on iOS and the other. And on macOS, how many of you are doing macOS apps? Oh, I did not expect that. I want to chat with you guys. The next thing we need to compare is linking. We don't really need to compare it because on Java it's not something you would do. So the easiest comparison for linking is in JVM, you don't do it. Real quick, the JVM does it for you when it's running, but unless you did something real wrong, you should never see the link something error. Like you could see it, but hopefully you won't. For linking, I wanted to focus more on the difference between static and dynamic, because that's something that I've struggled the most with, and I couldn't figure it out for a long time, because they are so fundamentally different, but it doesn't sound like it. It seems like they are like just a different way to doing the same thing, but kind of the same. So with dynamic and static, sorry, I'm going to go with static first. It's on the left. We have uncompressed archive. It's a .a, you could have seen that. Sometimes it doesn't have the .a, it's just the name of it. think of it as the object files I mentioned before, and put them together. It's that. If you put them in the directory, it would be basically the same thing. That's your static linking. It shouldn't even be called linking. It's like, it's not. You just put them together, and that's it. And the issue with that is it doesn't need linking to become executable, to even run. With dynamic, this is the final result of whatever you're doing. So it does go through linking. It needs to find either all of the symbols, all the stuff that you want to use, or you need to tell it, I'm not going to use, like, you're going to find these somehow in the runtime. So it's produced by linker, and it can depend on other dynamic libraries. It cannot depend on static libraries. The way dynamic libraries depend on static libraries is by including them. And that's when you can find those weird duplicit symbols. You run your app, and you have warnings all over, like, oh, this symbol is declared twice. It's undefined behavior. Which one's going to be used? That's probably because you had a dynamic, either a library or an executable, in two places, depending on the static library and including it. So why do we use dynamic? For mobile, it's a little weird, because like dynamic for mobile has different implications. For system libraries, dynamic linking allows them to be loaded once into memory and reused. So everything's faster, everything's cached, all good. It also allows you to have common API. So let's say you have an app that is somehow communicating with another app. If you have a dynamic library, you can be sure that in runtime it will be loaded. Like that one, the same one will be loaded between the two of them. If you use static, you may very well have different versions during your compilation, and so they won't be compatible with each other. And the two things is, dynamic is faster in compilation time, usually. And that means that the main reason for that is you don't need to link them. You just include them in your app. So once you have a dynamic library in your dependency, so let's say you have 100 of dependencies. You shouldn't, but let's say you have 100 of dependencies. When they are all dynamically linked, they don't contribute to your compilation time anymore once they're built. So Xcode, probably Xcode for you, will just take them and put them into the app. And then when the app starts, it will load them, and that's when the final linking happens, and you get a slower program startup. Let's talk about distribution then. We have our library, be it static or dynamic, doesn't really matter. JVM, we have jar files. I hope this is readable. We have jar files. Those contain your class files, so whatever you built, that's in there. Also resources, other things. On Android, we have the AAR, which is similar, basically the same thing, and that's a zip. On native, we have a framework. So that framework is the bundle, so a fancy directory. It contains the module, so like the library that's shared here. It contains some information like the info list, so resources, information about the framework, and then you have module map and headers. These two contribute to the API of your framework. That's how, so when these are loaded, Xcode knows and compiler knows what will be available to you from this binary. On JVM, it's done by the classes themselves. They declare the visibility of classes, of functions, well, not in Java, but you know what. So that's this really big difference between JVM and native, where on JVM you need to use reflection to get to stuff that you want to use that's not visible to you. In native, you really just need the header file to compile against it. And as long as the code is in the library, you can use it. Don't do that. It will bite you in the butt. I don't want to spoil too much. But you can, if you really need to. Sometimes you do have to like get around a bug maybe, and so you can just edit the header file, add to it, or create your own header file even, and expose stuff that wouldn't be normally available to you. Now we have our jar or framework. How do we manage dependencies? In JVM, lovely Maven, Gradle, maybe Ivy for some of you. No, I see someone like, no, why did you even include that? On native, remember I mentioned there's standards, there's infinite number of them. It kind of goes with dependency management as well. None of these are standard, and all of these are. For iOS and for KMP, the most important one, and I guess the only one, would be CocoaPods. For iOS folks, I should have included Swift Package Manager, but I didn't wanna. So the rest, they're more like C and C++ world. So I just wanted to show, like, in the native world, there's so many different ways to do dependency management, and they don't really work with each other. Right? So you often end up using multiple, and often end up with, well, doing your own management. You just take the framework, download it, and put it in the project, and pray that it works. The next thing I want to discuss is ABI versus API, something that in JVM we don't usually think about, at least not that much. How many of you know the distinction between two of them? OK, good. I'm not going to repeat everything you already know. So application programming interface, I think you all know what that means. That's what is available to you as a developer, and what the compiler sees as visible, or public. This is the stuff the compiler can use when compiling. The one thing that's often overlooked is that dependencies are also part of your API. They may not be, but when you use a class from a dependency and you return it, or you have like a property with it, it's part of your API. So if they break their API, it's going to break your code even though you didn't do nothing. Meaning as long as you update. But as I mentioned, dependency management on native is in this weird state. Then we have the ABI. So how many of you know what ABI is? OK, cool. So ABI is the structure of the binary code and how that all is called, how it can be linked together, how it can work. So part of ABI is all the public symbols. So symbols are all the declarations you have in native. So it would be your classes, it would be your properties or fields maybe, and your methods.
How does it relate to LLVM, ABI?
So ABI on like the lower level is about the architecture. So what architecture you're running on is also like ABI, because it's the binary interface of the platform. But then your own app has ABI as well. So ABI is more important for things like libraries, where when you have a library and you have a dynamic library, let's say, right? Static library different, but with dynamic libraries, you deploy a dynamic library, you give it to people to use, and now you change something in it, and you give them like, oh, there's a new update. If they redeploy without compiling their code, because the API didn't change, so the compiler will be like, well, there's no change, I'm just going to run with it. What can happen is that your app will not work, because it will call something that's not there anymore, even though the API didn't change. So that means that API compatibility doesn't equal ABI compatibility. And I have a few examples that I think are really fun. So let's start with compatible changes that are both API and ABI compatible. So we have a class, and we have a property or field, and we remove it. Because it was private, there's no way you could have used it. Well, there is a way, but let's not talk about that. Kotlin, right? There's basically no way that you could have used it, well, unless you use reflection, but that's on you. So if you compile against this new version, you don't need to do no code changes. Everything works. If you don't compile, and if you just replace the library, everything still works because your code is not using it. API and API compatible. Right. Let's start with API incompatible change. So in Kotlin, changing the generic argument, for example, will stop you at compile time and say, hey, no. No. But because JVM, and this, sorry, should have clarified, this is Kotlin JVM. Kotlin-Native, whole different thing. That will crash. That's even binary incompatible. But in JVM, due to generics erasure, in runtime, there's no such thing as generics, right? So it doesn't matter whether it's a list of strings or list of strings, it's still a list. So it's binary compatible. You can just replace the binary and everything works as it should. But in compile time, it will be like, nah, we are not doing that. Then is the other thing. So let's say this is again Kotlin JVM. This would be native as well, I guess. But we have the foo with no parameters. You have your code that's using it, perfect. And then the author of the library adds a default, a parameter for default value. In your code, nothing changes. You can just recompile. You will have no issues. But the classes that are generated, the structure of the ABI is different. What happens in reality is there's two new functions, one that has just the parameter and one that has this like $sign default in its name. And that one is used to decide, okay, what parameters did you include? What parameters should have their default value used? So when you're using that in your code, it's expecting to call foo with no arguments. So it's not giving it no arguments or nothing. If you replace the library and you run the code, it's going to try calling that, but that method no longer exists. It's just not there. So it's going to crash ABI compatibility. So keep this in mind. I keep drinking at the worst possible moments. Keep this in mind because like when you make changes, it's important for things like incremental compilation, right? So one of the reasons why having incremental compilation is so difficult is that you need to not only, like the API doesn't really matter for incremental compilation, it's all the ABI. But it's so easy to break ABI in native that incremental compilation is extremely difficult to do well, right? It's like every little thing in native, because native is so strict, can break it all without the code changing at all. Now we get to the fun part. We finally have it. We want to run our code. In JVM, we build a jar. We hopefully install runtime. We need to put it on the path, maybe. We need to set the Java home, whatever. Hopefully we get through all of that. All the jokes are already there. I'm going to repeat it. And run, works, perfect, great. Native. You think that when you have an executable, you just run it? It's not that simple. It really depends on how you build it, what you linked it against. So if you're using dynamic libraries, they need to be somewhere where it can find them. In macOS or iOS, when you're compiling them, it will do this embedding. So it will take them and put them into your bundle. But it's really easy to forget setting it to embed, and then everything runs on your machine in debug because you have those frameworks there. So oftentimes, like in simulator, it works. On device, it doesn't, because device doesn't have access to those frameworks. And so it's really easy to get to a point where this framework doesn't exist. Why? Where is it? So make sure to, when that happens to you, go and check if you have embedding enabled. So it's going to be like this framework, embed, or do not embed. And it's difficult to debug. Like, I'm not going to lie, I'm still struggling when this happens. Like, OK, you have your R paths, executable. Not going into that too deep. So how does native work? Why is it so different? I'm going to go again from compilation through linking to executing. So compilation, as I mentioned, takes your source files and headers. Notice that it does not take libraries. It does not care at all about other binaries. Only thing it needs to know is your source files, more importantly, one source file, and headers of everything around it. Then it produces an object file that is a machine code with undefined symbol references. Those mean that there's something in the other headers that you're using, and you need that to be in there, so you know it's gonna be there in the future. That's what linking is for. So linking, which I recently learned that linker and linking is just a shortcut for link editing. To me, that was mind-blowing. I see it had no effect on any of you. Like, yeah, we studied computer science. What are you talking about? Like, we all know about that. Anyway, linker takes those object files we just built with compiler. It takes static libraries, because those are object files, and dynamic libraries. It produces your dynamic library or an executable. It includes all your object files. It includes all the static libraries, or their object files. And then, for dynamic libraries, it includes load commands. Those load commands will be important later. The execution of native binary is really, really interesting. So what happens is that when you double-click on your app, the kernel loads your app into memory, just your binary, no dependencies as of yet. And then loads this tool, and I'm talking about iOS, macOS, tvOS. Just want to make sure Linux and Windows do it different. And then loads this dynamic linker into memory. And then it runs that. So before your code even runs, there's a different program that's running in your memory space. What it does are these steps. So it runs through those phases. So it starts loading all your dependencies. So all the dynamic libraries that I've just mentioned have the load commands. So it's like, I depend on Kotlin. Load that for me, please. So it's going to go and load it. And Kotlin will say, oh, I depend on that. So it's going to recursively go through and find every single one. Then it does this thing called rebasing, where for each of those dynamic libraries, you have, because it can put it anywhere in the memory, you don't know at compile time where it's going to be. It needs to go through the library, and anything that's like relative pointer to something, it needs to relocate that. It needs to say, OK, you're here in the memory, and you're asking for something that's 42 integers away from you. It's going to be there. Use that right away. It needs to do this because there's no such thing as a relative in runtime. So your executable isn't really executable yet until it goes through this phase. And you have the binding. It's another thing. When you use something from the dynamic libraries, you need to bind those symbols. You need to say they are there in the memory. So that's how it finds what functions to call, really. Until then, it only knows, I want to call this function. I don't know where it is. I don't know what's going to happen. Please tell me. So that will replace those links. Then there is Objective-C phase. We're going to skip that. It's not important for us. And initializer phase. So initializer phase in C and C++, and in Objective-C, you have these static initializers. They are similar to in JVM, where you have like the static initializer in your class. Not completely the same, but it's your own code that runs before main. So you can do like init, you can load whatever you need for your code. And then we finally get to our main code, starts running, starts going. Hope you all appreciate Bimo. I love him. Let's quickly jump into best practices. We're running a little late. Decreasing binary size. This now is getting us to KMP world. If you use a lot of exports, actually, how many of you use KMP? It's my team, and okay. If you use KMP, if you get to use KMP, make sure you export as little as possible. So exporting in KMP generates a lot of code additional to your Kotlin code that is used to make sure that you can call it from Swift. So there's a lot of Objective-C overhead that gets called. If you see intransitive export anywhere, and if it's set to true, remove that, make sure it's always false. 1, it doesn't work. 2, it will blow up your size and also compilation time. And also, make most of your types internal if they are getting exported. So if you only have your shared module that then gets built into the framework, everything in the share module that you're not going to use, and you know that you're not going to use it from Swift, make it internal. It will not generate those things because it's not going to get exported, and it will make your compilation faster and the size smaller. And then last thing, make sure you're measuring the right thing. With binaries, it's easy to like, oh, this is huge. Well, yeah, you're measuring debug binary that has tons of information you're not going to have in the final one. Or maybe you're measuring a universal binary, and that gives you 2 things in one, oftentimes, sometimes more, hopefully not. So make sure that you're measuring the right thing. There's tools available. I'm not going to go through them because that's a lot. To improve your build times, follow all the recommendations I just gave you for binary size. They matter. Make sure that you give Gradle plenty of RAM. Like, it guzzles it out. Like, Chrome is no competition for building Kotlin-Native. Only build the architectures you need in debug mode, or maybe even in release. So when you're building for debug from Xcode, make sure that you don't run all like debug and release and all the ARM and your simulator. It can easily quadruple your build time. If you have something like a stable library that you would use from everywhere, publish it to a Maven repo, even like a local Maven, because it will enable Kotlin to cache it. This will improve with incremental compilation going on, but so far this is the easiest way to cache it. If it's too big and you want to, like, you don't really change it, that's the way to go. And new iOS and new Xcode, they come with this thing called mergeable libraries. What they do is essentially allow you to, in debug, use dynamic, and in release, use static. So you get the benefits of both. So you don't have to relink everything when you're building, but in runtime, you don't pay the price of dynamic linking. The last thing is eliminating undefined behavior. That's not really a thing you get in JVM, usually, unless you're doing something really weird. In native, it's kind of like the normal. But if you're using KMP, just make sure that you don't depend on static libraries from multiple dynamic places. So when you have your executable, that's always going to be dynamic. And if you're linking to a static library to it, and you're using another dynamic one that links to the same static one, you're going to get duplicate symbols. What can happen there, and we have someone in the audience who's not paying attention and had the same issue. I'm calling you out, Nick. What can happen is, for example, you have tests. And your tests are 2 bundles, and they are both dynamically linked. If you include your Kotlin and you build it statically, it's going to be built into both your app and the tests. But they are then running in the same memory space. So the symbols are duplicate. What was happening is like calling something from Swift was crashing in a really weird place. Because some of the symbols were from the one package, some of the symbols were from the other package. Think of it as having 2 class loaders and trying to use classes in between them. It just doesn't work. It will crash. It will be like, oh, no, that class doesn't exist. And heed all warnings that you see when you run the app or compile it. They will oftentimes make sure that you don't shoot yourself in the foot, because it's like you have duplicate symbols. Well, that's the first thing you should be fixing before you're looking, why is this crashing? Lastly, if your company has a training budget, go and let them to subscribe you to TouchLab Pro. We have so many resources on, like, if you're an Android developer, this is how iOS works and how to do it properly. We have all the best practices that I mentioned, going deeper into how to measure binary size, for example, how to make sure that you're doing the right thing. In closing, if you are interested in Kotlin multi-platform, I would advise go and try iOS first. Just try build a simple app and see how it works. Try to add a dependency to it, see how that works. And if everything works, go and try Kotlin multi-platform. Doing that will give you more understanding into the native build process that you will eventually need to know. And minimize the exported Kotlin functions, symbols. I'm saying that over and over and over because it's so important. Build time, size, all of it. And most importantly, have fun with some weird problems along the way. Thank you for your attention. Do we have questions? We don't have time for questions. And I'm promising t-shirts. So if you do have questions, please catch me after the talk or anytime today or online. I won't get you a t-shirt if it's online. Just want to clarify that. But yeah, one more time, we released Sky. If you're gonna use KMP, I'm gonna say it's a must, and that's not an overstatement. Now open source, available to everyone. Thank you for your attention.